Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over how to figure out the Kp value of a reaction when you're only given the percent by volume and some other things. So let's get into this. Okay, so in this problem, we're asked find the appropriate equilibrium constant Kp for the reaction below under the following conditions. So here's the reaction they gave us. So we have a half SNO2 solid plus H2 gas in equilibrium with water vapor H2O gas and a half of the solid tin. And so first thing to notice is that the tin 4 oxide and the tin are in the solid phase, so they're not going to be part of the equilibrium constant expression. So the Kp expression is going to be Kp is equal to the concentration or pressure. In this case, since we're looking for Kp, it's going to be the pressure of the water vapor, right? So P H2O, oops, that's a big O, the partial pressure of H2O on the top, and then we have the partial pressure, we have hydrogen as a reactant that's going to go on the bottom, so the partial pressure of H2. So it's the ratio of the partial pressure of water vapor to H2. Water vapor is also known as steam, right? So this is what we need to figure out. This is what we need to use to calculate the Kp value given the conditions. Now let's look at our conditions. Okay, so we have A at 650 degrees Celsius, the equilibrium steam and H2 mixture, right? Steam and H2, we have H2 and steam, H2O gas, was 38% H2 by volume. Okay, so how do we figure out this problem? Well, what you have to notice here is that when we have volume percentage, we can assume for this reaction that pressure, the total pressure is going to be constant. The temperature for these are going to be constant because they're the same reaction mixture. The volume's going to be constant. So here we can see if we use the ideal gas law, we can compare the, let's see, PV equals nRT. So if we solve for P of, say, gas A times the volume, since it's the same volume, we're not gonna put A there, so it's the pressure of the gas. So same pressure. That we got the moles. So here we're going to look at volume A. So we're going to look at the ratio of the volume, see how the volumes relate to the other parts. So we have the moles of A, and then times R, which is a constant, times temperature, which is a constant. So here, we're going to assume that pressure here is a constant, right? So if under these conditions, if we compare that to the total pressure, we have the total volume, right? So we have the pressure multiplied by the total volume is equal to the total moles times RT. And so under these conditions, right, so if pressure is held constant, R is constant, temperature is held constant. If we find the ratio of these two equations, right, then pressure is going to cancel out, R is going to cancel out, temperature is going to cancel out, and then what we're left with is this equation here. So the volume of A over the total volume is going to be equal to the moles of A over the total moles. And so what we see right away here is that the volume is proportional to the moles. And if also you recognize that here, this VA over V total is the volume fraction, is where we get our percentage from, because if you take the volume fraction, right, so if I'm going to put it here, so we have the volume of some gas A divided by the total volume, right, that's a fractional amount of the volume of A with respect to the total. If we multiply that by 100, then we get the volume percent, which is what we're given. Also, to keep in mind here, what do you notice here? We have the moles of a certain gas divided by the total moles. Well, that is the mole fraction. Hopefully you recognize that as the mole fraction. So that is the mole fraction represented by this chi symbol, Greek symbol chi. So the mole fraction of A is equal to the moles of A over the total moles, which is also equal to the volume of A over total volume, which is kind of what we're given here. Okay, so these are equal to each other. So we could use that to help us convert. So if we rewrite this, right? So I just showed that the volume of A over the total volume is equal to the mole fraction of A. And if we manipulate this, we can find the volume of substance A. But we don't want to find the volume, we want to find pressure. So we know another equation that's very similar. The pressure of A is equal to the mole fraction of A multiplied by the total pressure. But I just showed you that this is equal to the mole fraction of A. So we can use this as our the mole ratio. So here, all I would need to do is divide this by 100, but I could also just assume that I have 1 atmosphere of gas. Now, notice they didn't tell us what the total pressure of the gases are. Well, I can assume any volume I want because we're working with percentages. So I can assume 2 liters of volume, or I'm sorry, pressure. So I can assume 30 atmospheres, 29 atmospheres, whatever the pressure is. I can assume any total pressure I want because the percentage is always going to be the same. So why not make our lives easier and just assume one atmosphere of the total pressure? So I can then assume 1 atmosphere of the total pressure here. So if I take 38% of 1 atmosphere, right? So 38% of 1 atmosphere, right? That's going to be equal to, so 38%. So 38% of 1 atmosphere is going to be equal to 0.38 atmosphere, right? So then that would be the atmosphere of, that would be the atmospheres of the, the pressure of gas A, which is going to be the H2 by volume. So if I plug this in, let's plug this in. So here, this is our mole ratio. Remember the mole ratio here, the volume ratio comes from the equation. So we have 38% is the percent by volume. Well, that's going to be equal to the volume ratio, the volume of H2 over the total volume multiplied by 100. Well, if I just divide by 100, right, then I get the ratio here, VA H2 over volume total is equal to 0.38. So now I can plug that into for my mole fraction, right? So here, the pressure of H2 is going to be equal to 0.38 multiplied by the total pressure, which I am just going to assume is 1 atmosphere to make my life easier. I could assume 100 atmospheres, it doesn't matter. So 1 would be the simplest. So therefore, the pressure of H2 is going to be equal to 0.38 atmospheres. Right? So that's probably pretty much what I was kind of showing here, but I used it in this example here to use the equation to clearly show where I got that from. So hopefully this makes sense. Now, since I'm assuming a total pressure of 1 atmosphere, to get the partial pressure of water vapor or steam, I just subtract that from 1. So 1 atmosphere, so the partial pressure of H2O is equal to 1 atmosphere minus 0.38 atmospheres, and so I get 0.62 atmospheres for water vapor. Okay, so notice that I was able to get the partial pressures of the H2 and the H2O without having to use the temperature. So the temperature was given to you, but sometimes you don't have to use all the information they give you, and sometimes giving you extra information is a way of kind of tripping you up. So be aware of that. Okay, so now all I have to do to get my Kp value is divide the partial pressure of water over the partial pressure of hydrogen. And so I'm going to write that over here. So Kp is equal to the partial pressure of water, which is 0.62 atmospheres, divided by the partial pressure of hydrogen, which is 0.38 atmospheres. So if I divide those two, I get, what did I get? .64 Kp. So Kp is 1.6 rounded to 2 sig figs, since I have 2 sig figs here. So that is how you get the answer for part A. Part B is the exact same process. So again, use this equation. So I'm going to erase this and start over. Now we can do under the other conditions, right? So here, so we're at 800 degrees. Now the equilibrium steam hydrogen mixture was at 22% hydrogen. So if I do the percent, right? So here, 22% hydrogen is equal to the volume of hydrogen over the volume total, oops, that should be H2, over the volume total multiplied by 100. So now I just divide both sides by 100, and I get 0.22 equals the volume of H2 over the volume total. So here's my volume fraction. And again, as I shown before, the volume fraction is the same as the mole fraction. So then I use this equation with the mole fraction, and so I go P, the partial pressure of H2, is equal to the mole fraction, which is the same as the volume fraction. So that's going to be 0.22 multiplied by the total pressure, which I'm going to assume is 1 atmosphere again. So I multiply by 1 atmosphere, and I get 0.22 atmospheres for the partial pressure of hydrogen. To get that of water vapor or steam, I just subtract that from the total, which is 1. So the partial pressure of H2O is going to be equal to 1 atmosphere minus 0.22 atmospheres, which is going to be equal to 0.78 atmospheres. And so now I can plug that back into my equilibrium expression for Kp, right? And I do the same thing. So last time, let me erase and give some space here. So here for part B, Kp is going to be equal to the vapor pressure, or the pressure of water vapor or steam, which is 0.78 atmospheres. And we're going to divide that by the partial pressure of hydrogen, which is 0.22 atmospheres. And when we calculate that out, we get 3.5. Again, rounded to 2 sig figs. And so now we can answer the third question, letter C. Would you run this reaction at high or low temperature for the most efficient reduction of tin 4? So here, this is tin 4, this is tin 4 oxide. So we want to reduce the tin 4 to tin. So we want more to go this way, right? So we want more of this to be reduced to this. So we want more of this. So we want, therefore, more favored products. We want the equilibrium to favor the products. We want it to shift left. So that means that given the ratio here, we want more water. We want more water vapor, which is on this side. So if we increase this, when we increase that as well, right? So we want a high numerator, low denominator, which is your hydrogen on this side, right? And the way to do that is to push it this way. So we want a larger Kp, and so therefore we see at 650 degrees Celsius, your Kp value is 1.6, but at 800 degrees Celsius, it's 3.5. So you get a higher Kp value at a higher temperature, so therefore the answer to C is you would run this reaction at a high temperature. And that, ladies and gentlemen, is how you answer this problem or deal with a problem like this. I hope you enjoyed this video. If you enjoyed this video, if you learned something from this video, if this was helpful in any way, then please like the video, share the video, hit that like button over there somewhere, or it's there somewhere. Find it, hit it. Also, subscribe to my channel. Please help me out. Hit that notification bell up there somewhere. Also, by the way, when you do click that notification bell, click all so you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. I would love to hear from you. Thanks for joining me, and have a great day.